Bonjour à tous. Donc avant que le cours commence, je vais dire quelques mots pour présenter le lauréat du cours Peccot de cette année, qui en plus du cours Peccot a reçu le prix Peccot, qui est quelque chose qu'on donne assez rarement en plus du cours. Donc Juan Esteban Rodríguez Camargo a fait ses études d'abord en Colombie, puis master et thèse à Lue Pan à Lyon, une thèse soutenue en 2022 sous la direction de Vincent Piloni. Et depuis 2025, il est Research Group Leader, donc peut-être directeur de recherche à l'Institut Max-Planck à Bonn. Ses travaux portent sur la géométrie analytique P-adic, les représentations des groupes de P-adic. En particulier, il a posé des fondements en introduisant une notion de représentation localement analytique appelée solide. Et il travaille aussi à des applications au programme de Langlands et aux variétés de Shimura. Dès sa thèse, ses travaux ont été très remarqués puisqu'il a démontré une conjecture de Calegari et Emerton qui décrit la cohomologie des espaces localement symétriques. Et donc ces travaux étendent à un cadre complètement général des premiers résultats qui étaient dus à Peter Scholze. Dans d'autres travaux, il a développé une version géométrique de la théorie de Sen-Tate. Et il a aussi récemment écrit un autre article où il pose les bases de la théorie des démodules en géométrie analytique P-adic, avec par exemple l'introduction d'un objet qui s'appelle le champ analytique de De Rham. Et puis voilà, j'ai compris qu'il y a vraiment beaucoup de notions fondatrices dans ces travaux. Et aujourd'hui, le cours Peccot, le titre, qui sera donné en anglais, P-adic D-modules and the P-adic Langlands Program. Et peut-être j'ajoute que d'habitude au Collège de France, on pose plutôt les questions pendant la pause. Je pense que c'est à la fois dû aux questions de prise de son, mais peut-être aussi une tradition. Donc, voilà, il faut il faut réserver ces questions. Je pense qu'il y aura une petite pause et puis on peut poser les questions pendant la pause.
Okay. Merci beaucoup pour cette introduction. C'est vraiment un plaisir d'être ici aujourd'hui, de donner des exposés sur mon travail. Alors que vous pouvez remarquer, le titre est en anglais, donc je vais donner l'exposé en anglais. Je suis désolé. It's going to be easier for me since the notes are in English anyway. So today, the goal of the course is to give some kind of introduction. This new theory on, let's say, on P-adic differential equations. Obtained via this object that we nowadays call this related RAM stack. Or maybe, let me say it in less technical words, via geometry, analytic geometry, and show some of its applications to the P-adic Langlands program. So today we, okay, be careful with the board. We'll have some sort of introductory talk, telling a little bit of the history behind these developments and how we arrived to some of these definitions. So we'll say that the departure point, at least from the modern point of view of how we reach this technology, was the work of Lue Pan. on local analytic vectors. Of completed cohomology. Where I would say his main achievement was that, well, one of the main achievements was that he managed to mix actual geometric representation theory with P-adic theory. So to give let me just here a more precise meaning of what he did, let me recall some important aspects from complex geometry and complex Hodge theory. So discuss something about complex Hodge theory. In few words, complex Hodge theory studies different cohomologies and the relations in complex analytic geometry. The theories in complex varieties. And maybe more than just studying cohomology theories in complex varieties, it actually studies these cohomologies via differential operators, differential equations, and so on. Let me just call it via differential geometry. So perhaps the two most fundamental cohomologies that are related in the complex Hodge theory are the so-called Betty cohomology. So you have X over C, some variety. You have the Betty cohomology. That can be taken with values in C. So this is nothing but shift cohomology. It can be shift cohomology. But also can be computed using the usual cellular decompositions of just the C points of the varieties and using the usual techniques on algebraic topology. Just singular cohomology. Now I need to go to the other board. So this is somehow a cohomology theory that is quite combinatorial or just purely topological by nature. There is another very important cohomology theory. So we also have the round cohomology. Which is defined as, well, there is a way to define it. In algebraic geometry, you can define as some kind of hypercohomology. Of the sheaf of the round complex. That's this holomorphic round complex. And the standard comparison between Betty and the rank homology tells you that if you take Betty homology of the C points of your space and you tensor with the complex numbers, there is some natural isomorphism with this homology that is defined using differential operators. In addition, this the rank complex it carries a natural filtration just by truncating the differentials in the complex. Called the Hodge filtration. That just let me write what it is. So it's a decreasing filtration. At least in the way the conventions are done. The filtration begins with looking at the differentials, the rank complex to the dimension of x. And then you just start dropping the objects in the left-hand side. X. So this is the fill 0 part, fill 1 part, and so on. So this filtration is quite relevant in, let's say, complex geometry because of the famous and fundamental theorem in the subject called the Hodge decomposition. So have the following theorem. So let x over c, just simplify this, be a smooth projective variety. Then by taking the rank homology and looking at this filtration, we get a natural spectral sequence from the graded cohomologies converging to that. So we have a spectral sequence with Tini's E2 page, but let me just not say the page because I'm confused. Where here we just get the cohomology of the graded pieces of these differentials, which is just coherent cohomology, or shift cohomology. That converges to just the rank homology of x. And this spectral sequence has the amazing property that actually just generates and splits naturally in this page. There is a spectral sequence that naturally splits. Producing the so-called Hodge decomposition. P plus hi the RAM of x just in the direction P plus q equal to I of HQ omega P. So this theorem, let's say for people maybe before it became a standard in the area, is actually a quite remarkable result because this, the rank homology is computed using a, well, maybe not so simple complex that involves differential operators, and somehow you can compute the cohomology of this complex, just the, again, boundary maps modulo this, well, the maps killed by the differentials modulo the maps on the image of the differentials. You can just compute it very simply by looking at a reasonable, much easier coherent cohomology of some vector bundles in U variety X. So this is actually quite surprising. The proof of this theorem, I should not move this board. Oh, maybe I should move it from here. Let me give just some very brief sketch of how this is proven. It's going to be more relevant for the next part of the talk. So, a sketch of ideas. So everything begins with this the RAM and Betty comparison. So we use the RAM / Betty comparison. So this is something that in complex geometry can be stated in a very clean way. It's just telling you that if you consider the constant shift on the complex analytic variety, given by the C points of X, then this the rank complex that you just define using holomorphic differentials gives you a resolution of this. Okay. So by just formal properties of homological algebra, whenever you have a resolution of this shift by the complex, then the cohomology of this shift is just the same as the Eiger cohomology of this complex. So you can maybe, well, once you know how homological algebra works, is quite simple observation. But then we actually have more room to play with this shift now. In particular means that, well, X of C is not just a complex analytic space. We can also look at this object as purely a topological space, or maybe a little bit better as a smooth manifold, maybe something in between that will suffice for us, as a real analytic manifold. We can see XC as a real analytic manifold. By just considering real analytic functions on them. In which case, we have another resolution of the shift that not just involves this holomorphic differential, but also an anti-holomorphic differential coming from the derivation for just the conjugate of the structural shift of this. Involving holomorphic and anti-holomorphic differentials. Called the Dolbeault complex. So this is now not just a complex, but a big complex. But let me just write down in this, and this is somehow, these two are some sense homotopic. Now you have partial and partial bar operators, where this double complex is obtained by PQ to be those kind of forms that locally are given by taking, let's say, this set 1, this set P, this set 1 bar, this set Q bar. So some complexes that locally in some coordinates that maybe mixing here, they just can be written as P wedges of holomorphic differentials and Q wedges of anti-holomorphic differentials. So the coordinates you can make sense. This delta is precisely just the derivation with respect to these ones, the holomorphic derivation. This delta bar is the anti-holomorphic derivation. Like if you write down things in coordinates, set x plus iy and set bar equal x minus I bar, then this delta set is going to be dx plus I dy, and this derivation around this, and this delta set bar is just dx minus I dy. Once you have like local coordinates coming for this complex structure. Right. So now that you, well, like it maybe, let me just write this. It looks a little bit strange that, well, you started with a small complex, then you make it a very small, with a complex that you make it a very concrete shift, that was just C, the constant shift. And now you're making larger again, and even more larger than it was before. Like you first pass from here to here, and then you pass from here to something much bigger that actually contains this somehow in secretly hidden there. So the point is that in some occasions, adding more complexity to the object simplifies the theory, which is a little bit ironic. So the key point here is now that, let's say the key point, well, the key observation, I would say is more than an observation, is the full important idea in the theory, is that this guy being the analytification of a smooth projective scheme. And let me highlight where projective carries a natural, what is called Keller metric. I hope I did. So there is some sort of natural metric, natural way to talk about norms in this X coming from some kind of universal construction coming in a projective situation. Let me not say exactly how this is built up. Maybe let me just say why it is important. So, well, using this Keller metric, you can now try not just to study this complex, but maybe study analytic properties in this complex, in particular, how big these differential operators are, like in terms of norms, how big they span or they contract things. More precisely, what you are going to look at for proving this Hodge decomposition is the called Laplacian. So now there is degree 2 differential operators. And let me put here elliptic. Which is called the Laplacian. Oh, I just lost it. Laplacian. That, if I do remember correctly, this can be written as something like this. Is minus this. I think it's that. That using this metric, well, that is going to be somehow unitary. So that is self-adjoint. It is self-adjoint for the scalar metric. Maybe there is some kind of science involving, but okay, let me just wake up that. So now you have some sort of elliptic operator acting on spaces which this is self-adjoint with respect to some kind of natural inner product. Then now you can start doing harmonic analysis. So once you are in this situation, you have a control of, let's say, the norms in that sense of these spaces of differentials. And then using analysis, you can isolate as a direct summand the harmonic forms of these differentials, the eigenvalues for this. The thing. And the geometry of, or maybe the analysis, underlying analysis of the eigenvalues of this operator would yield that deduce. If you look at this cohomology of just using this delta bar operator, is actually precisely this space here. But you can just isolate it such that this one comes from a direct summand of this guy. And let's say by the way things were built up, here you just have fixed holomorphic differential and you just are allowed to move around this anti-holomorphic differential. Then, because in complex geometry things are quite acyclic locally, this is nothing but the cohomology that we wanted to compute at the beginning here. P. Then you, using, again, harmonic analysis, prove that this cohomology, which is a coherent cohomology, has some kind of interpretation in terms of differential operator and, say, these scalar metrics. And then, because this space is obtained by some kind of eigenvectors from a differential operator that can be completely isolated from this Dolbeault complex, you will deduce the splitting of the spectral sequence from Hodge to the RAM. Just deduce the splitting. So a statement that could be made even just in algebraic geometry require working with doing actually non-trivial complex analysis to be improved, which was this the first proof on the Hodge decomposition using complex geometry. complex analytic geometry. So actually rely a lot in, again, working with norms and differential operators. Let me remark these two words, norms and differential operators. Well, of course, this theorem tells you more, tells you that actually this rank cohomology underlies something called a Hodge structure, which is, well, let me not specify what it is, but essentially it's some kind of decomposition in terms of holomorphic and holomorphic pieces in your vector space. In this case, these things are indexed by two integers that tells you how holomorphic and how anti-holomorphic these spaces are. This is precisely the spaces of harmonic forms. And that's, let's say, some kind of the departure point of what nowadays we know as usual Hodge theory. So there are more general versions of these theorems. In particular, there are versions where instead of just looking at differentials, at the rank cohomology of a variety, you can start look at the rank cohomology of certain local systems. Even you have some kind of relative versions where you look at some relative cohomologies of something called variations of Hodge structures, maybe some polarization, and so on. So this is just in the first fundamental theorem in the subject that opened the gate to many different well, let's say, applications in mathematics. Let me now move from the complex a little bit to the P-adic situation. What happens in the P-adic Hodge theory? So instead of having a variety that lives over the complex numbers, let's just start with a variety that lives over the P-adic numbers. And let us just keep the same assumptions that we had before, smooth projective, even though this is not so important. Maybe being smooth is more important than being projective. Then we need an analog, well, maybe saying before, P-adic Hodge theory is in charge of a study as complex Hodge theory, just cohomology theories coming from complex analysis. P-adic Hodge theory studies cohomology theories coming from P-adic analysis or P-adic geometry. So this thing studies, let me call P-adic cohomology theories. And let me just mention, well, there are several of them. You could even separate the subject in two, in integral P-adic Hodge theory. Where we use the fact that in P-adic geometry we don't have just varieties over the P-adic numbers, but actually we have integral models of them due to the non-Archimedean nature of the analysis. And also we have rational P-adic Hodge theory. Okay, this one maybe assumes that X admits some kind of integral model. This one does not require this and just want to understand the invariance or the cohomological invariance of X over QP itself. And there are different instances in these two. There has been a lot of progress in this direction in the last years. Let me maybe highlight the most recent importance advancements that goes in, well, different works, in particular in the definition of prismatic cohomology. That relates essentially all examples of non-existent cohomology theories in P-adic Hodge theory, integral P-adic Hodge theory, this crystalline, the Ram, et al., and so on. And what we do in the work with Anschutz, so maybe I should bring some names, Badmore Scholze, and we also have Bad Lurie. and Greenfeld that give a very amazing geometric interpretation of prismatic cohomology. And this work with Anschutz, Lepage, Scholze, we attempt to do a P-adic rational analog of this one, something that we call analytic prismatic cohomology. But these theories, they do have some departure points, so let me give this. Okay. So maybe one of the fundamental theorems in P-adic theory is the so-called Hodge-Tate decomposition. That, as you can imagine, is the analog of the Hodge decomposition we just discussed before in complex geometry. So we have this theorem. Defaultings for varieties, and maybe just generalized by Scholze, and there are other people, but I will refer mostly to the statement proven by Scholze. So we started with such variety over QP. Then, well, we need to compare different cohomology theories. Or one of them, of course, we wanted to compare maybe the rank cohomology, but okay, maybe the rank cohomology is, well, quite differential operators, and we wanted to compare it with some kind of Hodge cohomology, but this we already did it using somehow algebraic geometry and complex geometry. So let us relate more P-adic nature cohomology theories. So up to some extent, an analog of Betti cohomology will be étale cohomology. This has to be taken with a little bit of salt, but let me make the analogy for this particular situation. So we do want to understand this étale cohomology of this variety X, but something funny happens here is that in order to have a more geometric invariant, we do need to consider this étale cohomology living over this algebraic closure of QP, and then just the QP coefficients. One very important reason why these cohomologies are relevant is because they naturally carry actions of Galois groups. In particular, they are essential in studying number theory, arithmetic geometry, and Langlands programming. So let me give the statement. You can base change to the analog of the complex numbers in the P-adic situation. So this is just the completion of an algebraic closure of QP. And then you have a similar decomposition of the étale cohomology in terms of differentials, just shift cohomology. Differentials. I hope I did not screw up. This thing should be just this. Okay, I hope this thing's got the correct direction. Tuck, tuck, tuck. And this one lives over CP. So it's important to take into account these base changes. This is minus P. The composition of this étale cohomology in terms of, again, just shift cohomology of differentials, where this is what we call the Hodge-Tate cohomology. And the difference, one of the main differences that it has with respect to the Hodge cohomology is that there is some twists here that come from the cyclotomic character. This refers to some type twist. So this is a decomposition that is not just a decomposition of plain CP vector spaces, but actually is equivariant for the natural action of the Galois group. So in the complex situations, we don't have a Galois group. Maybe we did have for the real numbers, but it's pretty simple. If we were purely in complex geometry, there is no Galois group. So with replacement of that was somehow this Hodge structure on this. In the p-adic situation, we do have actions of this kind of group that are, again, quite relevant in the subject. And this decomposition still can keep track of those structure. So let me again just sketch the way of this is proven, maybe in the way that Schulze proved it. As you will see, this requires different techniques and technology than from complex geometry. So the proofs are not quite analog from one to each other, but that's in some sense part of the goal of the lecture, is to make a framework where these two proofs are quite similar, even though not exactly the same. So the idea of the proof. So in p-adic geometry, well, as we did discuss for complex geometry, we first needed to consider some kind of analytification into a complex analytic space, and then to do some sort of complex analytic geometry. Here we just have a scheme, so we need to jump into p-adic analytic geometry. So this can be done in different ways. We jump from algebraic to p-adic analytic geometry. Again, because we do want to consider a question which is purely p-adic analytic. And so this one, you can use different theories. So rigid spaces of Tate, adic spaces of Ouvert, or Berkovich spaces of Peccot. So there are different formalisms that allow you to talk about p-adic analytic geometry. Maybe these two, well, this one only allows you to talk about p-adic varieties. This one is more general and allows a larger class of rings, basically defined by some sort of p-adic topology or adic topology. That's where the name comes from. And this Berkovich spaces is far more analytic in nature, and maybe this one actually allows a uniform treatment of p-adic and complex geometry. So in some sense, this one is maybe better if you want to move around between different primes and also into the complex numbers. So let me just use any of them. Maybe this one is the one that is using the work of Chargé. So we consider this angle of QP. And let me just say as a rigid space, a p-adic analytic variety, where I do mean a rigid space or adic space. Okay, so now that we have jumped to p-adic geometry, we are maybe in a little bit better formalism. But then we face a problem that we did not have in complex geometry. What the problem is? Well, in complex geometry, in some sense, the local structure of all the spaces is rather trivial, in the sense that locally, any complex analytic space is just a disk, or maybe a product of disks. So let me write this. Local geometry. Complex varieties, analytic varieties. It's rather simple. All of them are just products of disks. Well, local geometry of p-adic varieties is considerably harder. So there is some price to pay. There's a conservativity of difficulty in mathematics. In complex geometry, maybe the analysis is more complicated because making things converge requires more work. But things locally, at least geometrically, are very simple. In P-adic geometry, analytically, well, things are very simple. You just go something to 0 and you get something that converges. But then the geometry of these varieties is more complicated. So that's a problem because, well, we did use this feature in complex geometry to prove this Hodge decomposition, meaning this is the key in the comparison just with Betty cohomology, that everything is just locally acyclic. So here we need something else. So this is where, well, maybe many mathematicians appear, let's say Fontaine, and maybe more recently Scholze. Tells you that, well, the local geometry in P-adic analytic varieties is hard because you are just restricting yourself to work with P-adic analytic varieties themselves. But if you allow to work with a larger class of objects, geometric objects, then things, even though not trivial, becomes much simpler. So let's say the geometry becomes some way simpler, even though not trivial, by allowing a much larger spaces called perfected spaces. So say a standard technique that comes from Tate and Fontaine and Colmes, many classical treatments in P-adic Hodge theory, is that somehow the theory becomes much manageable if we start taking p-roots to the coordinates that we do have. So some kind of concrete example is, well, the prototypical rigid space that we use for these kind of things is just the torus over QP. That, in the language of this, is basically just the space associated to the ring given by a Tate algebra with this one. So basically just functions in the disk. Circle. Somehow just functions of norm 1. And, well, making analytic covers of this is difficult, but there are very simple perfected covers. This cover, the perfected disk. QP may be cyclotomic, which is obtained by, well, first maybe passing to the cyclotomic extension given by adding all the p-roots on QP, and then taking all possible p-roots on space and somehow making this a Adic space. So, there are a lot of different reasons why passing to perfect order spaces is quite powerful. Let me slowly give this reason by continuing with the discussion about the Hodge state decomposition. So using these much larger charts in some sense of your space that, again, in a first sight does not look that acyclic, but they do, they are very acyclic. Scholze defines something called the proetal side of X. And then one of the theorems that are proven there, which is, well, up to some point is almost a tautology, or it's not a tautology, let's say, it's not so hard to at least prove this, is that this étale cohomology of QP bar with QP coefficients, and even let me just put ZP coefficients, is just nothing but the pro-étale cohomology in the pro-étale side. With ZP coefficients. But in some sense, this ZP is some kind of ad hoc construction that is obtained by taking some limits in mod ZP to the n cohomology, while this one is actually an honest shift cohomology. This is kind of honest shift cohomology in a site. Again, if you think what it is, if this one is defined by just taking limits of étale cohomologies, of étale shifts, and this one is just taking the pro-étale cohomology of pro-étale shifts, then well, you just put pro in both sides and then you just get it. Yeah, of course, like making all the formalism work is not easy. In particular, developing the perfect space is a lot of work, but once you do have the theory passing from this to this, it's not hard. What is much harder and less trivial is the following theorem. Let's say, let me just go to Scholze. Maybe again, file things on Scholze. So this is called the primitive comparison theorem. And this says that this pro-étale cohomology after you do the base change from CPU to OC, and here I think I do not need anything weird. This is just the same as the shift cohomology of another shift in the pro-étale side that we call O hat. So this is basically the structural shift in the pro-étale side. And maybe I'm lying to you and I should put an almost here. And maybe this is not a shift, but an almost a shift. With almost means almost mathematics. Well, in the sense of all things, not like. So you should think of this theorem think of this theorem as the analog of controlling metrics, or controlling norms of differentials. Using the Keller structure. So in other words, in the complex situation, we do have a first key point that we have a Keller metric that allows us to somehow control norms of differentials. In that situation, using a differential operator was the Laplacian. In this case, we do not have yet differential operators, but at least we do have some kind of natural norms coming from these integral models of shifts. And these norms are good enough to allow us to control, well, you used to think of this as some kind of represented by some kind of chain complex, and these norms allow us to control the norms of these chain complexes such that we can put this shifting side here. In other words, the way you prove this is actually by using some kind of Cartan-Serre argument as for the finiteness of coherent cohomology in complex analytic varieties, but with this shift instead of just the structural shift of the complex analytic variety. So you should think of this actually just as controlling norms in P-adic theory. So this cohomology here maybe I should say that this is also Galois equivariant. This cohomology here maybe after you invert P, is what we call, which is nothing but the cohomology of the full structural shift, so the one that you obtain by just inverting P here, is what we call the Hodge state cohomology. And well, this theorem somehow tells you that Betty cohomology can be computed after you base change in terms of Hodge state cohomology, similarly as saying that the rank cohomology or Betty cohomology can be computed in terms of Hodge cohomology. And now the other part that is non-trivial in this P-adic situation is, again, theorem of Faltis-Scholze, that this cohomology is actually what we wanted to do before. Just a direct sum. P plus Q equal I of HQ with CP omega P with a Tate twist coming from P, which is this Hodge state, computation of Hodge state cohomology. However, the way you prove this in the previous situation, it was rather clear that once you look at the Hodge complex that was coming from this graded piece, you somehow just end up with cohomology of the differentials. In the P-adic situation, coming from here to here is again a non-trivial step. So this one is a non-trivial step, controlling norms, and now this one to this one is another non-trivial step. And roughly speaking, the idea of this is you first think what happens locally in coordinates. Let's look at coordinates. In this case, the coordinates are, again, just let me ignore torus. We have this torus here obtained by taking all roots, which is a set P1 torsor. With this one is just the Tate module of roots of unity, just because this is an étal torsor given pro étal torsor given by roots of unity. And then the theory of perfect ordered spaces tells you that this kind of cohomology for period shifts that we call in this pro-étal side, they're acyclic. So that's the cyclicity that we use in the P-adic situation. So in the complex situation, the cyclicity comes from the constructibility of the spaces. In P-adic column geometry, the cyclicity comes from the cyclicity of period shifts on perfect ordered spaces. So the structural shift in this pro-étal side. So just thanks to this acyclicity, you can compute, let me write in the right notation, the pro-étal cohomology of the torus with O hat coefficients, just as group cohomology, continuous group cohomology. With values in just the pro-étal cohomology of this, of the perfect order evaluated in this, which is nothing but the coherent cohomology, so the global sections. In this case, it's rather simple. It's just CP D1P infinity. So now we are in a situation where, at least locally in coordinates, maybe globally is more complicated to jump from here to here, but at least locally in coordinates, we just need to compute some kind of group cohomology. So there has been a lot of interest in computing, in just developing theories of continuous cohomology for periodic groups due to many, many, many reasons. I mean, this one is one of them. And the theory of Tate and Sen, so to compute this, usually we use the theory of Tate and Sen of some kind of decompletions by traces. To actually give a concrete computation of what this object looks like. So this is maybe one of the points that occur in P-adic Hodge theory that is quite different from complex Hodge theory is that in the complex situation, okay, we did have the Keller metric that was the way to deal with norms. In this case, we have these integral models, which are the way to deal with norms. But then in the complex situation, we have differential operators. So by studying differential operators, that we ended up with Hodge decomposition in the P-adic geometry is by studying continuous cohomology of perfect Hodge spaces that we end up with this Hodge state decomposition. So there is something that is not completely analog in both cases. So the techniques are quite different. And in some sense, the Lue Pan tells you that you can actually also do this step of computing these cohomologies via some sort of differential geometry after passing to maybe locally analytic vectors in some sense. So maybe I should put Pan and Sen and Berger-Kolmes. Tells you that you should pass to kind of locally analytic vectors. So this is just a way that, as occurs in, for example, the study of automorphic forms, often they are defined using some, let's say, unitary representations of real groups, but then within this unitary representation, there are some nice vectors that do admit the action of differential operators, in particular automorphic forms, they do admit action of differential operators. And a standard procedure there is just to pass to some kind of subspace of smooth or analytic vectors in there. In the P-adic case, we can do exactly the same. We have some sort of unitary representation of ZP1 in here. And then we can consider some space of vectors that admit differentials that we call locally analytic vectors. And by doing so, at least now we have access to differential equations coming from the Lie algebra of this P-adic Lie group. And these traces, again, allow you to somehow tell you that there is no illusion information when you compute cohomology in these two ways. And well, this is what we call Sen theory. This is the completion of this kind of cohomologies by local analytic vectors using these traces. Was interpreted by Berger-Kolmes maybe in this way, using local analytic vectors. And that's the key piece that Pan has expanded from just a purely local computation to a more global kind of nice theory using these Sen operators, geometric Sen operators. So I'm going to mention more about the relation of, let's say, the work of Pan, and concretely a way to rephrase a big chunk of the work of Pan, maybe the geometric input and not the applications to the language program, by discussing the case of the Modular curve and how the complex and the P-adic, let's say, natures of Hodge theories of the Modular curve can be, in some sense, interpreted in exactly the same way. But maybe for that, we first do a small break, 5 minutes, and then we continue. All right, so let's restart. So as I said before, we're going to maybe see more a concrete example of these Hodge decompositions we discussed before in the case of the Modular curve. And well, this maybe is in particularly convenient for me because this will allow me to actually talk about the work of Lue Pan in a more precise way. So certainly his work is more in the P-adic aspects of this theory, but to motivate a geometric way to interpret his results, let me discuss what happens for the complex situation, which you can do exactly the same. So let me be quick with some of these things. You consider the half space. Let's see. Upper, lower. planes. So these things are actions of GL2 of R, just by Möbius transformations. And this action is transitive, and the positive matrices, meaning the matrices with positive determinant, leaves stable the upper half plane. And even the stabilizer of I is precisely the group of SO2. Just isomorphic to S1. Right. Well, there are maybe a lot of talks already motivating these spaces. These are some kind of moduli of elliptic curves with a trivialization of the homology. There can be interpreted in terms of variations of Hodge structures and so on. Let me not do that now, just saying that this is related with elliptic curves. And then, well, you define, as usual, these arithmetics of groups. Let me just call the congruence of group. Maybe in the positive determinants of Q. Basically, if it is not far from GL2 set, meaning that if the intersection with GL2 set has finite indexing both. Then from this, you define what is called the connected modular curve of level gamma. To be this quotient. And as usual, maybe you wonder, well, this kind is maybe not acting totally discontinuous. They could have some fixed points, but basically have finitely many of them, so it doesn't matter for constructing this as a complex analytic variety. But maybe just keep in mind that if gamma is small enough, so for example, it's one of these congruence groups, so to set mod n. If it is one of these congruence groups, then for n bigger than 3, then there is no problem. This thing acts totally discontinuous. This quotient is a complex space. If there is torsion, well, you can just take the coarse quotient, or you can just take the stacky quotient. I prefer the stacky quotient because it's going to save the correct information. But just forget about that. Just imagine that you're working with this level. So these guys, they do carry, they do admit some sort of compactifications. X gamma by adding what we call cusps. So I think that the usual picture of these things is something like I don't know, you have, I don't remember how many holes I want to add, but you have something like this. And I mean, I do not know if this one actually exists, but you should imagine that the y is something like that, and then the x is just closing these things together. Again, I do not know if this one is concrete modular curve, but it's some pictures like that. So as I said, these things can be understood as moduli of elliptic curves with level structure. So So in particular, if you take yn over q, the moduli of E with PQ, a basis of the n torsion of the elliptic curve, then the complex points of this is not one of them, but it's a disjoint union of one of them. That's why these ones are called connected. So it's that disjoint union indexed by elements in Z mod and cross of y gamma n. And well, basically, the index depends on the pairing being equal to this kind of thing called rate pairing to the exponential of 2pi r over n. So depending on how these things are well positioned, then you get something like this. Maybe it's worth to say that if you have some tau in H, then the elliptic curve associated to tau is nothing but the quotient of the complex by Z plus tau Z. And in this case, this P is going to be maybe just 1 over n, and this Q in this component is going to be maybe R tau over n. Just maybe give a little bit more of a concrete example in mind. So this is nice. Why do we care about modular curves? Well, there are many reasons. Maybe one of them is because we can define modular forms, and modular forms are analytic functions that carry a lot of arithmetic information. And the best way to understand modular forms, or maybe to think about modular forms, is just at least of integral weight, is just by looking at sections of line bundles. So we have an universal elliptic curve that even already exists on H. It's just this quotient that mentioned there at each point tau. And there, this universal elliptic curve is a particular abelian scheme, so it has a section which is the zero section, and we can define this modular shift as the differentials pull back at the unit. And then for k in Z, we can just define the omega k to be the omega e tensor k. So, well, global sections, you can write it down as functions in the upper half plane, satisfying appropriate congruence relation for the Mobius transformation, which is maybe the usual definition you find in the literature of modular forms. Let me not write it down. What is important is that maybe just taking global sections here is too large. So you want to have some control on how these things go to infinity. And this is done thanks to some kind of canonical extensions. And this canonical actually has a precise meaning. X gamma. And then you can define spaces of modular forms of level gamma. Maybe complex modular forms of weight k and level gamma. To be just the global sections of this omega k. And then you can define cusp forms by just putting some zeros at infinity. So in terms of algebraic geometry, this is written as this. Yes, cusps. But this is just the cusp divisor. normal radius. So this COPS is just a bunch of disjoint points. In particular, it's just defined by an ideal, a principal ideal, and you're just taking things that vanish at those points. Okay. You have other important constructions in the theory of modular curves. Maybe one of them is the construction of automorphic local systems. What we have? And let me write down maybe just the kind of the universal one, and all the other ones is constructed by taking symmetric powers. So you have, again, this map f from E to y. So you can consider the relative P-adic cohomology. With values in Q. And this is a kind of a Q local system on Y gamma of rank 2. So this is basically saying that pointwise you just have the P-adic cohomology of a modular elliptic curve. And elliptic curve, the complex variety is just a product of two circles, and well, this one has H1 just of rank 2. You also have the rank comparison. Meaning that if you take this P-adic cohomology, again as a sheaf on this guy, and you tensor with the complex numbers, you actually compute the relative de rank cohomology, holomorphic de rank cohomology. Right. So this is more than just a, well, maybe I should say probably more like that. This is the zero sections of this, if you're more precise. Yes, where this nabla is the Gauss-Panning connection. On this relative rank cohomology. So these are just relative versions of this relation of this computation of the Hodge decomposition that we discussed before. So these relative versions I mentioned. Maybe last remark that it's important for the following is that, let me first say this. So this guy, it is not just a connection, so it's not just a vector bundle with a connection. It actually carries a natural filtration. Again, as we discussed before, it's coming from the Hodge filtration, maybe relative of this morphism F. So we have a Hodge filtration. Coming from, I think this is maybe like this. This one is maybe like this. If I do not mess up, I think that's fine. And all this structure, all this, maybe just say this in degree 1, and this one in degree 0. And all of this the structure, this kind of connection and filtration, they will naturally extend by theorem of the linear and so on, tous and to the compactification up to a span of maybe adding some kind of logarithmic poles in the connection. Right. So these cohomologies are important because maybe of the following, I should have noted this. Very, very, very important theorem in the theory of p-adic modular forms, which is the Eichler-Shimura decomposition. Theorem, let me say Eichler-Shimura. And let me put Faltings because Faltings generalize this in for arbitrary Shimura varieties and basically arbitrary automorphic local systems. Meaning that here you could take not just this, but symmetric powers of this, and instead of just looking at Shimura varieties, you could look at Siegel spaces or maybe other, modular codes, you could look at Siegel spaces and any other fancy Shimura varieties, and here is where the Faltings comes up. And Rowley tells you that the cohomology, let me just discuss the H1 of, let me say the petit cohomology. I think maybe that's the one that's more convenient for me right now. Of the modular curve with values in this local system after your base change to Q and C. It has also a Hodge structure where the holomorphic part is just the global sections of just the modular shift of level 2. And the anti-holomorphic part is the H1 of just the structural shift that using Serre duality can identify with the H naught of x gamma of the omega 2 minus cosp. So maybe more classically, you find that the composition is in 2. I hope it's just a 2. Did I mess up something? Should be a 3. Sorry, very likely just mess up the indexes, so let me just find here. Is equal to 3. This should be a 3. 2 minus 3 should be a minus 1. And now we're fine. Yes. Gamma C. This should be now a 3, and this should be a minus 1. Right, fine. Something like that. So there are different versions with the same case of this, and if you put same case, then you're putting here k plus 2 and maybe minus k, and we'll get like k plus 2 and k plus 2 if you put same k. So for k equal to 1, this is k plus 2, it's just 3. So why this is important, so let me just say maybe a few words. So this is highly important. For the construction of Galois representations. cuspidal forms. Of weights k bigger than or equal to 2. So the point is that when you start looking at the sin case of these things, this naturally just splits in two copies of, well, basically just the automorphic forms of level sin k, k plus 2. So k can be at least 0, so this one can be at least 2. This equivalence is going to be Hecke equivariant after you normalize the Hecke operators in the appropriate way. So these Hecke operators just basically arise from correspondences of moving the level in the modular curve. Maybe more naturally, it's just a residual action of the GL2Q action on the upper half plane after you take some kind of cohomologies. So you do have such a kind of Hecke decomposition. And this Betty cohomology you then compare with étale cohomology of the rational modular curve, the one actually coming from algebraic geometry over Q, which carries a Galois action. So then you're able to jump from some representation with a Galois action that is what you want to attach to modular forms. Then you can start cutting off eigenspaces for these Hecke operators that does not change which version of this cohomology you take, either étale, Betty, the RAM, it doesn't matter. For this Hecke action, they're all the same as an abstract representation. And then by just isolating appropriate eigenspaces of dimension 1 in here, you get something of dimension 2. You get something of dimension 2, and then you get that two-dimensional Galois representation after passing to étale cohomology. Then it's a matter of using other techniques to identify trace of Frobenius with maybe the eigenvalues of the Hecke operators, which maybe is a different matter, but okay, this uses the so-called H-Leschimura relations and so on. But somehow this is one of the first key ingredients that is used. This ingredient, you can rephrase in a different way. This is nothing but the Hodge decomposition of this. Instead of taking as Euler-Shimura decomposition, so this is nothing but the Hodge decomposition. Of cohomology of automorphic log systems. So maybe in the case of H1, it's maybe not too complicated if you write down things explicitly, meaning that you're already in a situation where you only have two pieces, like this omega E and omega E minus 1. Then this minus 1, of course, you will relate it with this minus 1 after coming from the H1, meaning the H1 maps to the H1. And maybe there is some kind of funny other thing coming from this guy that, well, you should think of this maybe as omega 1 tensor with the differentials of x adding divisors at the cusps using the Kodály-Spencer isomorphism. And if you imagine once you go to the rank complex of this connection, then one of the terms that's going to show up is precisely this one, at least as a direct summand of the H1. And then, well, you just look at differential operators, spectral sequences, and you end up with this. Things get more complicated when you start taking symmetric powers. So in particular, you don't have just two pieces in the filtration, you have a full range of pieces in the filtration. And then study this becomes more tricky. But let me tell you that actually there is a quite clean way to understand the Hodge decomposition on these local systems. So maybe there is a first step saying that this Betty cohomology agrees with Hodge cohomology. So let me this. So to prove this, you first using just kind of general facts in Hodge theory. You prove that this Betty cohomology of this, again, Betty local system tensor C is just the same as the Hodge cohomology of the associated Hodge local system in some sense of the modular curve, which by definition is just the graded pieces of the de Rham complex, of the de Rham local system. So this is just the, if I say it's Hodge, it's because this carries some kind of a structure called Higgs bundle, and maybe you actually taking secretly this on E's and having some log structures, but let me just ignore this. This is a Hodge in the Rham. So because the Rham filtration satisfies grid field transversality, you can just pass two graded pieces in the Hodge filtration, and then you end up with something called a Higgs field, a Higgs bundle, maybe. And this one, the feature is that now the differentials are linear instead of just differential operators. They're actually linear maps on the variety. And in principle, computing this is a matter of computing some kind of complex of coherent cohomology and coherent cohomology of the variant. So again, this just follows from nonsense in Hodge theory, meaning that this guy is some kind of variation of Hodge structure with polarization, and this just yields this sort of general results. And what is left is to compute this. And maybe I want to focus in computing this. Again, this part is just general nonsense in Hodge theory, and this part is the actual, this one is non-trivial, but this one is the tricky computation, let's say it this way. In the sense that if you try to do this for more general Chimoire varieties, this is the problem you're going to encounter. You may just have used some kind of general facts in variations of Hodge structures, you go from this to there, and then you're stuck in trying to compute this by hand. But actually, and this is the idea coming from Faltings, that Hodge cohomology can be computed using, again, differential operators, of course, but not just differential operators, but actually some very particular ones that come from something called a BGG resolution. So let me say here, Hodge cohomology, so Faltings. Cohomology of Chimoire varieties can be computed using differential operators arising from the so-called BGG resolution in the category O of G of 2. So this is just some kind of a standard category of Lie algebra representations that has been considered, well, some kind of way to try to understand Lie algebra representations. There are a particular very nice class that has a lot of good finiteness properties that allow you to understand this very well, even and gives you some sort of natural resolutions of algebraic representations in terms of more simple objects called Berman modules. More simple, maybe not so clear, but in some sense, algebraic representation, just resolution for scenes which are induced purely from the torus, from just abelian codes. So trying to make this dictionary as fast as this will be maybe impossible for me right now because I do not remember exactly the conventions that he did. So let me instead just give you a different geometric perspective on what he did here. And for that, I will going to start moving to objects that I'm not going to define, but that I will give an intuition of what they actually mean. And that will be the goal of the course, is to define in a more precise way these objects and actually somehow give you an idea how to use them to study differential equations and so on. So well, we want to, again, transport some kind of category O to differential operators and then move into the Chimoire variety. And maybe if you hear me to talk the last couple of years, you've seen that I say a lot this word Ramstack, and that I'm a little bit obsessed with these guys. So let's interpret this. Falting's proof. Using, and let me just put in code analytic, the Ramstacks. And the Bellison personal localization. So we'll need some notation. So start with GL2. And in GL2, I do have two Borels, B bar and B. So this one is just the lower triangular Borel. B is the upper triangular Borel. And T is the diagonal torus. In principle, like, well, I mean, well, let me just definition. From these two Borels, I can produce two flag varieties. Maybe something that is called flag standard in initial Hodge theory, which is GL2 mod this Borel, and flag that is just GL2 mod this Borel. And both flags are just isomorphic to P1. Like you can just move this one to this one by some kind of conjugation anyway. So both iso to P1. But I do want to understand these objects actually keeping track of the combinatorics that are behind this choice of this and this. Meaning that I want to see as co-representing filtrations decreasing. Filtrations in O2, where this one is field 1 and this one is field 0. So precisely those filtrations that occur in the Hodge filtration of the relative to rank homology of the elliptic curve. And this one, I want somehow the opposite of this are going to be this increasing filtrations V inside O2, where this one has field 0, and maybe this one has field -1. I hope I did not mess up this. Maybe I want this one to have field 1 and this one field 0. I always forget exactly. No, I think this is fine. Field 0 and this one should be field -1. So this is just inspired from the filtrations that occur, let's say, in the Hodge decomposition of this relative cohomology of the elliptic curves. Like you do the combinatorics, I think this is what kind of conventions you end up having. Let's not focus too much on this. Let me just say what's important is that you do have two embeddings. As topological spaces, let me say. One of them from this thing into this standard flag variety. So this one is the one that is going to be holomorphic, because corresponds to the Hodge filtration on the elliptic curve. And there is another embedding that corresponds to the conjugate of this Hodge filtration, which is anti-holomorphic. So then something funny happens in this theory of analytic geometry is that in the complex situation, this if you have a variety over C, there are two things you can look. You can look at the topological space and see it as sheaf, or basically just sheaves on the topological space. In analytic geometry, this is reflected by something that we call Betty stack. You should think of this as just the topological incarnation of this object in analytic geometry. And there is another object, which is what we call the analytic RAM stack, which in some sense is a sheaf or analytic space that witness some kind of regular D modules on X. And these two actually are the same. And this is something that maybe Schulze called the analytic Riemann-Hilbert correspondence. Telling you that some kind of the RAM information is just the same as topological information. So, having these maps of spaces, let me tell you basically how you can reconstruct H from the RAM stack and these period maps. Or maybe let me just state what I want to state. So then you have this sort of anti-holomorphic map, again at the level of Betty stacks. Which makes sense because we just need to have a map of topological spaces to define this. And of course, this one you just can compose with the natural map that you have from the holomorphic. Upper half plane. Then this theorem of Faltings that witness, again, all these BGG decompositions and so on, you can rephrase it in the following. So there is a diagram. No, let me say Faltings plus epsilon, meaning all the works you need to make sense of this. In analytic stacks. Let me just maybe say that this diagram is actually GL2 Q equivariant. If you just take the H plus, and again you just compose to this the RAM stack that let me write it out this way. Now, one important feature of this the RAM stack is that it leaves, the flag variety has a natural torsor from the torus, which is just basically the sheaf of modular forms seen over the flag variety. So this one will leap over the classified stack of this RAM stack. And then modular forms, they do lift to the upper half plane. The modular sheaves, they lift in here. So you actually can, let's change it, and construct a direct map in here. Well, this flag variety also has some kind of natural Borel torsor. And sorry for writing BV, but that's the choice I use for the Borel. And you can just wonder what happens when you pull back along here. And then it turns out that what you want to find here is something that we call just the Hodge stack. Now, these two, and well, this one ought to be Cartesian. These two, the space it has another interpretation coming from the theory of the Bellingson-Bernstein. This is something that is just this twisted D modules. So basically, sheaves on here are just some kind of D tilde modules which are twisted by this length bundle on the flag variety. This one actually you can write down as just the quotient of basically the Lie algebra of GL2, maybe some sort of action. Let me just call it here. Some infinitesimal action. The Lie algebra. That, well, we just translate in analytic geometry, and well, concretely, this is some kind of neighborhood of one in GL2 that you should think of this as some kind of geometric incarnation of the action of the Lie algebra. And therefore, you can forget to just the point modulo this GL2 action. And this one is basically the same as GL2 representations. So this thing is a stack that you can write down concretely. It's just H modulo this tangent space, maybe after taking some kind of completion at 1 or over convergent neighborhood at 1. So these things compute Hodge cohomology. Well, this map, I'm going to say maybe just in words because of the time, is given by, well, if you look at this Higgs field that you wrote here on the modular curve, it carries a natural filtration just by looking at degraded pieces of the Higgs, of the Hodge filtration of the rank cohomology of the elliptic curve. And it turns out that as a Higgs field, it has a natural ascending or increasing filtration. Well, because the Collier-Spencer map kills the correct cohomology. So this increasing filtration you get actually tells you that this guy carries a naturally reduction to a torsor over B itself. Again, maybe not, I mean, it requires maybe some bookkeeping here because of time, kind of bit precise. But somehow this is just coming from the fact that once you pass to, again, the Higgs field, then you now have an increasing filtration and not just a decreasing filtration as a Higgs field. And in particular, if you start with something like the standard representation, if you want to compute the Hodge cohomology of the standard representation, the thing that corresponds to the relative Hodge cohomology of the elliptic curve, you can just pull back here. This is precisely this Higgs field associated to the standard, to the rank cohomology of the elliptic curve. You can push it down here. But just nonsense in 6 functors tells you that this is just the same as pulling, pushing, and here. And then going from here to here is basically what we call to be the Bellin-Solbersan localization. Then somehow using just what we know about the Bellin-Solbersan localization, in this case, it's just the Borel-Weil-Vaught theorem. Then we know what exactly the standard representation we localize in this flag variety is going to be just 2 line bundles with the appropriate degree that I wrote before. I think would be O3 and O-3, something like this, in the correct degree. And then this localization will be reflected when you pull it back here. And that is essentially what explains these H-Shimura decompositions in this more geometric way. Sorry, it's a bit of a mess, this diagram. So what Lue Pan tells you is that, well, this thing that exists, maybe let me just write a cleaner diagram. So let's take gamma and model by this. Then instead of writing this, you can write down the modular curve of level gamma with this Hodge stack. You have this modular curve. You have a little bit of a fancy map to this gamma modulo this FL the RAM tilde. You have a fancy map to maybe something that I'm going to denote this way. It's nothing but some kind of over-convergent neighborhood of gamma inside of GL2. So something that knows about the gamma equivariance, but also about the Lie algebra action. And well, this one I'm going to denote it like this. So in this way, you can just descend what you said, but directly to the modular curve. And then the theory of Pan on decompleting by locally analytic vectors and doing geometric set theory and then proving this, or studying this cohomology on the modular curve has the following shape if you rephrase it in terms of analytic geometry. Again, plus epsilon. So there is, so let me maybe just take one of these levels of the modular curves. And again, this y n over q, directly over Cp, modular curve. Let me just call this Kp level, this one K. Let me just take P prime. Let me just take this P prime. Which version do I want to do? Okay. Let me just do it like this. And this one is just going to be this P-complete version of that, just the Iwahori level, I think. It's just matrices. Or maybe it's not Iwahori, but this one is just the kernel of GL2 set P to GL2 set mod P. Then Pan tells you that there exists a diagram in analytic geometry where here you can put the modular curve of this level. We call it KP. You have some kind of weird Hodge state map, which is analog to the Borel embedding. We're now to model by something that we call QP smooth. So in some sense, here was not differential information, but was discrete. Here there is no differential information, but because it's profinite, you need to keep track of the topology. So it has some kind of smooth representations, or smooth functions in here. You can pull back to this locally analytic quotient of QP, and now you end up with a Cartesian diagram that is just a Hodge state stack. But then you can just forget about this. And maybe just as a last remark, this localization, well, produces for you in particular some kind of analytic torsor in top of this space. And what Pan tells you is that this torsor is nothing but the infinite level or locally analytic vectors at infinite level. So by looking at the infinite level modular curve and taking the completion by locally analytic vectors, and again, taking into account all the period maps and all the hidden P-adic Hodge theory that I say here. So for example, geometric N theory for the modular curve, you could rephrase it saying that this square is a Cartesian or something like that. So this will tell you that this N operator, that is basically just this stack, in some sense, that's the N operator, the geometric N operator, comes from some kind of Lie algebroid cohomology here. Is just saying that this map is Cartesian, just coming, basically this differential information is coming from this differential information and so on. The fact that, I don't know, this completed cohomology can be computed as coherent cohomology here is, well, maybe a little bit slightly different, but basically everything comes from this diagram. So the goal for the next lectures would be to start discussing more about this theory of analytic RAM stacks, how they are defined, how this Hodge state stack is defined, how this prismatization is defined, and how this Cartesian square is just a piece of a maybe more fundamental Cartesian square that, at least for the modular curve, can be directly constructed, which is related with this Scholz's conjecture of the existence of the Zigusa stack, which was proven by Zhang for PL and Daniel Zhang for Homestead in maybe Hodge type or Brilliant case. So that'll be the goal of the rest of the lectures, and I think I should stop right now. Thank you.